Good night, everyone. Fluid mechanics, forces, applied force to the gate. If we consider a gate with the width of B and we want to calculate the force which applies from a dam, for example, if a discharge of Q is coming from the upstream and moves to downstream, we want to know what is the force applied to this gate. So if we consider a control volume in the neighborhood of our gate in upstream and downstream south, so this is our control volume, and then study the forces which applies to this control volume. So in the upstream side, which is H1, we have a distribution of pressure from 0 to gamma H1 in the upstream side, and also gamma H2 in the downstream side to our control volume. And also, if you want to convert that to a force, force times an area is a pressure times an area is force. So the average of this one is a half of gamma h. And then if you just consider a width of unity, if you consider b is equal to 1 and h is equal to h1, so that's a half of gamma h times h1 times 1. That's our area. So it just turns to be a half of gamma h1 squared. Likewise, for the other part is P2A2. This is F2, force is equal to pressure times area, or sigma times area. That's a half of gamma h2 squared. And we also have like a force like S from the gate to the control volume, and based off Newton's second equation, the same amount of force is applied to the gate from our control volume. So we can call R is reaction applied force to the gate from the control volume, which we are looking for. S is applied force to the control volume, which is here. So if we want to, after creating this control volume and study the forces on each side of our control volume, we then can just jump to a momentum equation from any um, fluid mechanics textbook or a FE or PE reference book in section 6.2.4.3. That's impulse momentum principle, like summation of forces is equal to a rho q delta v, because a rho remains the same in your fluid. And then if you expand it, it just says summation of forces. We already know our forces is P1A1 for our control volume minus P2A2. This is our positive direction. So positive X direction is our positive. So this is F2. This is F1. This is F2. And also S, if you remember, S was applying to our control volume. This is our S. And then R is here, which is the gate from the control volume. So in our control volume, we have these forces and as soon as we got S, we have like R, because they are identical to each other. And in the other side is rho Q delta V. So we have rho Q times V2 minus V1. And just consider we calculate Q like for that's Q discharge for unit widths. And if we want to multiply, and if we want to calculate it for a, like for example, if you have B like 10 meters, then you apply that force R by 10. But we use the discharge for the unity first and then multiply the reaction force by the width of our gate. So in such case, we can replace P1A1 by a half of gamma H1 squared, likewise minus P2A2 minus S is equal to rho Q difference between the velocity in either side of our control volume, upstream and downstream. So you can rearrange this equation based off S, which is the force to the control volume, which is exactly equal to reaction or force applied to the gate from the control volume. So if you just replace S by R, it just gives you, well, this is the force for the unit bits of your gate. And then if you definitely you want to uh, know, for example, for 30 meters like bits, you have to multiply R prime is R times like 30, 20, whatever your bits is. This is the unit force. So let's put it into an example. So in our problem, in below channel, in upstream side, we have a discharge like, consider this one like Q. These are identical because we are calculating, then this is like for 10 meters. In below channel, in upstream depths, we have upstream depths of 6 meters, downstream of 2 meters, incoming unit discharge of 3 meters square, 3 meter cube per square per meter, and we want to calculate the applied force to the gate. So that's R, but for 10 meters, this is 10 meters of the gate. So R prime, if you calculate R for unit widths, then multiply it by 10 meters, it just gives you the answer. So based off what we talk about, the applied force to the gate is for unit widths is a R, and that's a half of gamma H1 squared minus half of gamma H2 squared minus rho Q velocity in the downstream minus upstream. So in our case, if we do know that the rho of water is 1,000 kg over meter cubed and G, these are provided by problem statement, and G is almost 10 meter per square second. It's the exact value is 9.81, but just in terms of simplicity, we just consider it 10 meter per square uh, second. So then Q is A times velocity. Likewise, discharge for unity, A is Y times B. If B is 1, A moves to Y, depths of water. And in such case, V1 is Q over Y1 and V2 is equal to Q over Y2. So in such case, if you replace the numeric value, Q is a 3 meter cube over second, 3 over 6 a half, 0.5 meter per second V1, and V2 is a 1.5 meter per second. As expected, V2 should be higher than V1. And then if you replace it in the reaction force equation, it just gives you gamma is rho G, G is 10, it's half of 10 to 4 times H1 is 6 squared minus H2 is 2 squared minus rho 10 cubed times Q, which is a 3 times V2 minus V1. And if you do the math, it just gives you R for the unit of volume is, the unit width is 157,000 pounds. So R was the force for unit bits as we talk about. Then if you multiply this force by 10 meters because we want to calculate for a gate, and the bits of our gate as you can see here is 10 meters. So if that's the case, if you simply multiply that by 10, it just gives you 157 times 10 cubed times 10, it just gives you 1570 kilonewton in terms of force applied to the gate. You can also solve this problem in with a different approach, and we call that like solution 2 is a specific force method, and that's based off this equation. In next video I'm going to solve this problem with a far simpler approach based off hydraulic. Thank you. We'll see you in next video.